Hello, everybody. I'm here today to present a paper entitled Confirm, Evaluating Compatibility and Relevance of Controlflow Integrity Protections for Modern Software. So I'm Xiaoyang Xu, and this is a collaboration with my lab mate, Masu Wenhao, my advisor, Dr. Hamlin from University of Texas at Dallas, and Dr. Lin from Ohio State University. So Controlflow integrity enforcement is a great idea pioneered by Abadi and other co-authors back in 2005. And the main idea is to prevent people from hijacking software with their kind of guard code that restricts the target of Controlflow transfers, either at compile time or source agnostic binary to binary transformation. So this is a lot better than, say, fuzzing to try to detect hijacking vulnerabilities, because CFI can precisely enforce Controlflow graph policies, where fuzzing just sort of probabilistically detect possible faults. So here is a timeline of research into CFI, along with software fault isolation, SFI, and vtable protection. So CFI was invented back in 2005, and there were a series of follow-on works that improved depend on it, providing better precision, more accurate policies, better performance. And starting from 2014, there has been a complete explosion in the number of CFI, because there are some really, really hard problems getting to work efficiently on lots of architectures and different applications. For example, one of the hard problems is how do you implement CFI when you have a lot of objects with writable method tables floating around? And one of my prior works, object flow integrity, was tackling that problem. And another example problem is, can you somehow use typing information to get the enforcement better? And there are several works that work on that. One of them is TALCFI. So we have made impressive progress tackling all these problems. And there was a survey paper published in CSER 2017 that summarizes the prior CFI works. And if you want to read more about CFI's precision, security, and performance, you should definitely read this wonderful paper. And it was inspiring to us for this work. So although with this harvest of CFI solutions, we are not aware of any work that can fully secure, say, Microsoft Office suite. So why is that? So to answer this question, we have surveyed a total of 54 CFI papers from 2005 to 2018, published in the top 4 security venues. Among these papers, 94% of them are evaluating on Linux, and only 4% of them are evaluating on Windows, that reports experimental results for at least one complete non-benchmark application. So we have all been there building these great technologies. And of course, there's a hope that these things can eventually protect us from terrible cyber attacks. But unfortunately, we look at what cyber criminals are actually attacking. And here's a list of top 10 in 2018. So among these top 10, 8 of them are Windows-specific vulnerabilities, and including 5 Microsoft Office bugs and 3 Internet Explorer bugs. And if you go on to look at larger lists, see top 20, top 30, they are basically all Windows-based vulnerabilities. So these are the actual compromises in the real world, but they are by far dominated by Windows compromises. So what I'd like to do, and I think every CFI researchers would like to do, is to be able to block those attacks. Those are the ones that are happening all the time, the ones someone stealing your credit card information. But actually, this is not a surprise. When you look at the market share of desktop operating systems out there, you can see that about 98% of desktop operating systems are non-Linux. And even in mission-critical environments, we got the same picture. And here are some reports we collected. So according to DOE, about 75% of control systems are running Microsoft Windows XP, and more than a quarter of all the government computers currently run outdated Windows or Mac OS. Various agencies currently store their secret information on outdated Windows 2003 servers, and there are hundreds of satellites running Windows 95 above our heads. So this is the real world. It would be a great thing to hit if we can protect all the things with the existing CFI solutions. And I think there's an expectation on the side of us researchers that we can simply take the CFI solutions and apply them to Windows applications with a little bit engineering. But as the technology is reaching great majority, we and everyone are finding out that is not true. And this is hard even to find out why the Windows and macOS applications are breaking, because when we try to apply existing Linux-based CFI solutions to them, because those are usually closed source ecosystems, we don't have source code for most of the binary code that breaks. So like those CVEs, they are proprietary web browsers and Microsoft Office that we don't have source for, or libraries that are closed source. So this is a challenge in front of all of us, and how do we surmount this? We conclude that the problem is usually something to do with compatibility. So the system might be secure if only the software works after you apply the CFI algorithm. The difficulty is figuring out what broke in this piece of complex software. So in the past, we sort of dodged this problem because we have conducted most of the evaluation in terms of security and performance, but there hasn't been a systematic study of the compatibility problems. That's why we don't know what they are. And there's a lot of aggressive testing done with CPU benchmarks, but those are probably good for performance testing, but still not reveal what the compatibility problems are. Because CPU benchmarks, I think we all agree, are not representative of the Controlflow graphs of, say, Microsoft Word. Those are very different programs. So in order to cope with these problems, we propose our solution, Controlflow Integrity Relevance Metrics, confirm. In our paper, we identified a total of 20 compatibility problems that are challenging for CFI enforcement. And based on these problems, confirm is the first testing suite that is designed specifically for CFI solution evaluation. And using confirm, we reevaluated 12 public available CFI implementations. And overall, we got about 53% success rate in solving the compatibility problems. Then in the end, we did a correlation analysis between confirm and the CPU benchmark suite. So confirm is now publicly available on GitHub. Please download it, check it out if you're interested. In order to study the CFI compatibility limitations, we laboriously disassembled and debugged CFI algorithms applied to many, many large, complicated, closed-source software products. And as a result of this hundreds of man-hours of testing of these things, we were able to come up with 20 categories of what we call widespread classes of CFI compatibility problems. So here's the list. On the right-hand side, there are some of the software products that we found these things in to show you these are real things, not some pretend compatibility issues. And it would be obvious, very difficult to simply apply your CFI algorithm to Adobe Reader and it breaks probably for 7 different compatibility reasons. You don't have the source code for it, it's very complicated. So in order to make this job much easier for researchers, so we have developed toy programs that each exhibit some of these compatibility problems. In this chart, the toy programs are listed on the left. For each of them, we applied 12 major CFI solutions to that and use it to try to evaluate whether that solution is compatible with that problem. We give it a cross mark if the test program reports either compilation error or crashes at runtime, meaning incompatible at all. And we give it a warning mark if it passes compatibility check but fails security check. And depending on which program it is, because some of them can double as microbenchmarks, they give performance results. So when a task succeeds for one of those, we report the performance overhead as a percentage. If there's no performance number, we just give a check mark. So many of these reported failures or warnings are probably very easy to fix. The reason why they went undiscovered when the paper was originally published was because there wasn't any easy way to test all these things. And that's what we're trying to do. We're trying to provide that. But on the other hand, some of these are really hard problems that maybe nobody can solve. So we don't know how to solve them, but they haven't been studied very much because there hasn't been the test suite to show what they are. So I don't have time to cover all of them here today. Let me give you some examples of each. Let's start with how a CFI algorithm protects returns. So in this program, both the functions authenticate and print prompt cause the same subroutine f. So we want to make sure that if it is print prompt that is called in f, it better returns back to itself at line number 10 of source code. Because if we allowed it to return to the call site in authenticated at line 4, then suddenly it got authenticated. Then at assembly level, as we know, the return address is pushed onto the stack and pointed to by the ESP register. And usually the way almost all CFI applications work is that they find dangerous instructions, like this return instruction at line number 12, and then they insert some kind of guard code here to prevent that from going to a bad place. And usually the guard code logic is something like this. If the return target is going to take is invalid, then abort. Otherwise, continue. But we need to be careful before saying whether a return target is valid or not. First of all, we need to make sure that it returns to call sites. But we also need to remember which call site it was. Because obviously, if you don't restrict it to call sites, well, then it returns to arbitrary address and got authenticated. But if we just restrict it to call sites, but not the precise one, we still have the same problem. It got authenticated by just calling print prompt. So one of the ways to implement that return guard is to use a shadow stack. And let's see what happened here. In this program, the main function calls f, and f calls g in the try block, then g calls function h. By far, the shadow stack code is maintaining a separate stack at the same as the regular call stack. And now in h, it throws an exception. The way that the low-level binary code works is that there's something called stack unwinding that occurs, where things get popped off the regular stack until it hits the call frame, which consists the correct catch block. And in this case, the call frame of function f. So suddenly, a whole bunch of frames go away without any return executed. And the shadow stack implementation somehow has to know that this has happened. Otherwise, these call frames are not going to match up. But it turns out to be very hard to implement a shadow stack that works in this way, because there are so many different ways that a whole bunch of frames can be get popped at once. In fact, it can be done with a single assembly instruction that just adds a number to the ESP register. How do you find that instruction and differentiate from all the other ESP adding instructions that just popping off one frame? It's very difficult. So we call this problem unmatched call return pairs. And here, when the return instruction from f to main is executed, the return guard code checks whether the return address on the shadow stack is equal to the one on the regular call stack. And then this benign program aborts with policy violation. Now we look back to this table. And yes, all these software products have that problem in there, including PDF Reader, Apache Web Server, Microsoft Office, web browsers. So they all break when you try to implement CFI in this way. And another problem that seems to be hard to fix is multithreading. Multithreading is now extremely important for software efficiency, but it can be problematic for CFI enforcement. Because it turns out that in Windows and macOS, all the threads have write access to each other's stacks. They all live in a flat address space. So a compromised thread can overwrite the return address of another thread between the check and the use of that return address. So it's a time to check to time to use vulnerability. We call this a cross-thread stack smashing attack. So here, thread 2 is being protected by some CFI solution, and the hijacker thread 1 here tries to overwrite the return address of thread 2 to some dangerous address in an infinite loop. It's just waiting for the right moment to exploit this talk-to window. And we found out that using this, we can break every CFI sandbox we tested. We're not aware of any way to fix this problem except by introducing huge performance overhead, maybe a randomized safe stack, but the performance of that is like 1,000% or something. It's very hard. So another widespread source of unsolved problems we discovered is that there's a lot of code out there that does runtime modification to itself. And it's not just G compilers. Even if it was just G compilers, that would be a problem because there are lots of languages that are now becoming G compiled, including Python, Java, C#, etc. But there are some programs that are runtime unpacked, little use components. And there's even self-hooking behavior. And this is a reason that nobody has successfully applied CFI to the entire Microsoft Office suite. Since we developed the confirm tests, and we then had a set of micro benchmarks for which we can get a bunch of independent performance results, we decided to try to answer a long-standing question that we had, and that is, to what degree do Spec CPU benchmarks exhibit code features that are even related to CFI? Because some of them have really simple control flow graphs for which almost no protection is needed. And so when we get performance results for those, it's not necessarily representative of what the performance would be on a real large application with complicated control flow graphs, like, say, PowerPoint. So we did a correlation analysis from confirmed scores versus Spec CPU performance scores in the presence of CFI. Then we came up with this table. So the correlation analysis results are listed in the right, ranging from -1 to 1. One indicates that the overhead of a Spec CPU benchmark and confirmed overhead medians are most direct related, and -1 indicates most inverse related. So you can see that almost half of them even have negative correlations, and an overall correlation of only 0.36 on average shows that Spec CPU benchmarks might consist largely of code features unrelated to CFI overheads. So we're not saying that CPU benchmarks are not predictive of real-world overheads, but if we rely primarily on Spec CPU benchmark overheads to assess performance of CFI, then we might be getting misleading results because lots of those programs don't have features that we know are present in large programs, and that significantly affects CFI overheads. Okay, to conclude my talk, we found out that compatibility of CFI solutions are understudied. This is because of the difficulty of figuring out various compatibility problems hiding in large, complicated software products. And we also found out that CFI implementations are commonly evaluated in terms of performance and security, and CPU benchmarks are widely adopted for CFI evaluation. We therefore proposed Confirm that covers a set of 20 widespread classes of CFI compatibility problems, and Confirm is the first testing suite that is designed specifically for CFI testing. Then we use Confirm to reevaluate 12 publicly available CFI implementations. In the end, we did a correlation analysis between Spec CPU benchmark suite and Confirm. So again, Confirm is publicly available online. Please check it out. Thank you.
Hi, Justin Kapos, NYU. First off, I want to say I really like this work. I think this is uncomfortable work for a lot of people who published in this space, but it's very necessary work that they probably should have done themselves, to be honest.
Thank you.
So have any of the systems that you studied been deployed? Did they, in their papers, present any information about practical deployment or use outside of just testing on spec benchmarks and other toy examples?
I'm sorry, can you say it again, the question?
Did any of the papers that you looked at have results where they talked about a practical real-world use of their CFI system at scale by actual customers?
Sure, there are some of the papers we do a very great job. Like I think one of this Lockdown and some other works that reports lots of experimental results for large, complicated software products.
So, but is this a production use? Because I'm curious if a large company uses this in production, part of what I'm taking away from your talk is that it feels like they would have found a lot of these issues that you're describing. Is that the case, or am I misinterpreting your message?
I think so, yeah.
Okay. Thank you.
Aditya from Minnesota. So I was looking at one of your slides which was mentioning exploiting the talk-to window for cross-stack smashing. I just have a question on how this exploit works. Like, was this a valid exploit or no? I think you a bit further. Yeah, the slide. So I just want to know how, is this a practical exploit or is this just a proof of concept that you're suggesting that this exploit might exist?
We applied this one to the 12 CFI works, and it actually broke all of them.
So this particular idea would be used to any software, would you suggest, or does this require any specific, are there any specific prereq that this attack would work on? The talk-to window, exploiting the talk-to window.
I'm sorry, what is it again?
So my question is this. Since you said you tried this exploit on 12 different exploits or 12 different entities. So my question is this, how can you generalize this idea of a talk-to window that's also doing a cross-threaded stack smashing? So how is this idea scalable to any other potential talk-to window?
So we just want to show that multithreading is a problem for CFI enforcement. So this is kind of a proof of concept attack.
Okay, thank you.
Drew Dean, Amazon.
Okay.
Can I ask for some more specifics on your spec benchmarking? How many iterations of the benchmarks were you running on a machine with one socket or more than one socket? And was ASL R turned on?
You're talking about confirm or spec CPU benchmarks.
Yeah. What?
This one? I mean
Yes, I believe so.
So what is it again?
The details of how you ran the spec benchmarks, like how many iterations were you running?
So we try to let each program running for around 5 minutes, but it is configurable if you look at our GitHub.
Okay.
Yeah.
Thank you.
Thank you.
All right. Let's thank him again.
Thank you.